Welcome to our course on interactive computer graphics. This is our course introduction. Let me first describe what we mean by interactive computer graphics. First, this is not about real-time rendering. This course is about interaction. And specifically, we discuss interactive techniques and systems for visual problem solving. So let me describe what we mean by visual problem solving. So visual problem solving, we mean all visual aspects of human intelligence. And I think visual problem solving consists of three parts. First, you have to understand incoming information. And then you have to come up with a solution about the problem. And then you have to communicate the idea to the other people. And this kind of visual problem solving appears everywhere in both professional and daily activities, such as, for example, medical doctors plan surgical operations, or coaches teach how to play sports. And product designers, architects design products and buildings. And fashion designers design garments, and then a scientist trying to understand nature. And all these activities involve intensive visual problem solving. And our goal is to make these processes more efficient, productive, and pleasant using computer technologies, leveraging interactive computing. And let me now describe what we mean by interactive computing. So let me compare interactive computing with old-style command-based interaction. So old-style interaction is command-based. So user gives command to a system, and then system does a task, and then user sees the result. And this is kind of asking a computer to do something. But interactive computing, we mean more like an augmentation of human activities like this. So user continuously works on a problem, and then system continuously provides feedback. So this is the kind of working style we want to emphasize in this course. So interactive computing is to augment human intelligence by providing rich feedback in very rapidly and very fast. And so it continuously provides feedback, and then it accepts intuitive input, and then provides intuitive feedback. And then behind the scenes, system tries to do some intelligent computation. And in this course, students will learn how to do this using your system. So let me situate our course in a broader context of computer science. So computer science field roughly is divided into two fields, theoretical field and the applied field. And among the applied field, our course is related to two subfields called graphics and visualization and human-computer interaction. And so this course can be seen as an introduction to these computer science subfields. And let me show you a couple of topics we discuss in this course. So first, we will discuss improvements to traditional graphical user interface. So we will describe how to implement window operations, scrolling, icon manipulation, and so on. And then we move on to 2D drawings. So we will help you how to draw illustrations, and then also how to move them. And then next week is 3D modeling. So we will describe how to create 3D objects using two-dimensional input devices. And then we will discuss how to handle deformable objects such as clothing and robes, and also flexible objects. And then in the last 3 weeks, we move out of the screen space and then go to the real world. So we first discuss how to create physical objects out of a three-dimensional model in a computer. And then we will discuss how to leverage physical simulation to produce functional products. And then finally, we will describe interaction techniques to work with computers or systems interacting in the real world, such as robots. And this course is basically a case-based learning. So each lecture introduces example of systems. And then exercise help you obtain deeper understanding about the topic. But of course, these are just sample examples among many, many infinite possibilities, and they are just starting point for further exploration. So at the end of each topic, I will show information and pointers for further research, further study by yourself. So in this course, throughout these examples, students learn what we can do and also how we can do it with interactive computing. Hello, this is Interactive Computer Graphics Week 1. The topic we discussed this week is Graphical User Interfaces. Graphical user interface is windows, icons, menus, and so on, and it turns computer control problem into visual problem solving. So whenever you interact with computers or your smartphone, you always have to solve some visual problem solving. Visual problem. And this lecture, this week, we introduce 5 attempts to improve current graphical user interface operations. And here's a list of topics we discuss here in this week. The first is scrolling interfaces, the second is manipulation of desktop icons, and then pointing by mouse cursor, and then handling of digital ink. And then finally, we will introduce a technique for voice interaction. The first one is scroll interface. The work we introduce here is called speed-dependent automatic zooming for browsing large documents. And the problem we want to address here is that navigation of a large document is difficult. Currently, dominant techniques is scrolling and zooming. So scrolling is usually use a scroll bar. However, it can be tedious sometimes to control very small knob. And you can also use a rate-based speed-dependent scrolling, but it's very hard to control when you're moving too fast. And typical approach is to use zooming interfaces to large documents, but you have to combine scrolling and zooming and can be confusing. Let me describe with specific examples. So here is an example. Okay. So here you have a very long document. And then if you want to scroll, you first acquire a very small knob and then you start dragging. However, if the document is very long, very small mouse movement causes a big jump and can be difficult. And also, a more difficult, important problem is that this kind of chapter structure is not visible. So if you want to go to, for example, chapter 9, it's very time consuming to find chapter 9. And another possible interface is rate-based scrolling or speed-dependent scrolling. So you press wheel of a mouse and you get this widget, and then you can start scrolling with controlling speed. And it's okay when you're moving slowly, but as soon as you move too fast, you have no idea of what's going on. It's very difficult to navigate. For example, if you want to go to chapter 6, it's very hard to do it using this interface. And the similar problem happens in other applications. This is an example of map navigation. And again, if you're moving slowly, it's fine. But as you start moving faster and faster, it's very hard to understand what's going on. So typical approach is to manually zoom out and acquire target and move and zoom in and move and zoom in. But you have to go back and forth between scrolling and zooming, and it can be very inefficient and tedious. And now, so what we propose here is to automatically zoom in and zoom out depending on your speed. So if you are moving, you start from slowly and then moving fast and then slow down. And as you change the speed in this way, system automatically changes the scale of the screen. So in this way, the user can navigate through large information space just by controlling speed. So let me show you a demo again. So here's the same program, but here we enabled automatic zooming. So when you're moving slowly, nothing happens. But as you move faster and faster, system automatically changes the scale. So here, your speed in the information space is very fast now, but thanks to the zooming, the pixel flow speed is constant. And then you move faster, and then acquire target and slow down. So in this way, you can navigate through a large information space very smoothly and efficiently. just by controlling speed. And you can do the same thing with web browsing. Again, without zooming, if you move fast, it's very hard to understand what's going on. With automatic zooming, when you're moving faster, system starts to shrink. So here, your speed is already very fast. So it can be difficult to understand what's going on without zooming. But thanks to zooming, pixel flow remains constant, and then you can keep track of what's going on. And in addition, the system makes chapter structures visible. So it's very easy to go to a specific chapter using this interface, like chapter 4. And these techniques can be very useful for other applications too. So this is an image browser. And again, without zooming, it's very hard to understand what's going on. So neighboring, adjacent, snapshot, and then next, and then 2 blocks. It's very hard to understand what's going on. But with zooming, system automatically zoom out depending on speed, and it's very easy to understand what's going on. Next image, or then 2 images after this or not. So this is like reading a very big newspaper. When you are reading here and moving to the next, you go to see the entire overview and then go to the next. And this interface naturally represents this kind of interaction. So that's a demonstration. And let me briefly discuss some implementation issues behind the scene. So the basic algorithm is very, very simple. This is a governing equation, basic equation. So a scale multiplied by speed remains constant. So which means if your speed is faster, speed is larger, scale gets smaller, and then speed is smaller, and then scale gets larger. So it's so simple and easy to implement. So this ensures that the perceptual scrolling speed on the screen remains constant. However, this naive implementation has some problems. So 2 problems: sudden zoom out at the beginning of scrolling, and then also abrupt swelling at turning the directions. Let me describe one by one. The first one is sudden zoom out. So let me describe here. So naive implementation of this technique is first we set speed proportional to mouse movement as in standard rate-based scrolling. And then scale is calculated based on the equation 1. So here's a diagram. So you change the mouse position, and then speed linearly increases based on this equation. Speed equals constant by dy, mouse position, and you get the speed. And then based on the equation 1, you get this speed. However, look at here. As soon as you start zooming, scale suddenly drops. So this sudden drop is very, very annoying if you actually interact with the system. So, but thinking about zooming should be exponential. As you move your mouse, scale should be multiplied with the same ratio each time. For example, as the mouse moves here, and then scale bits half, and then as you move faster, and then scale bits and a half again. So revised implementation is that scale is exponential to mouse movement first, and then speed is calculated based on equation first. So here's a diagram. So as soon as you start scaling, then scale is exponential function of mouse position like this. So this will show very constant smooth scaling. Then after that, you compute speed based on the equation 1 as a inverse proportional. And then this way you will get a very smooth interaction as shown in my demonstration. And then second problem is abrupt swelling or turning. Suppose you are moving downwards first, and then you moved a mouse upwards, and then you change the directions, and then go up, and then release. And here, as you change the direction, velocity inevitably temporarily becomes 0, which means that scale equals suddenly 0. which means that as you change direction, screen abruptly gets larger, which is very, very annoying. So one possible solution is like this. So we introduce delay in scale change. So as you change the direction, then zooming scale changes slowly. And then when you go back to the original speed, and then scale will be recovered. So this way you will get a smoother interaction. So that's a brief description of the paper we published at UIST 2000, titled Speed-Dependent Automatic Zooming for Browsing Large Documents. And here is a couple of pointers for further study. So one is zooming interface. Zooming interface is a very interesting popular topic in user interface and computer graphics research fields. Original paper was published as at SIGGRAPH 93 by Ken Powering, and you can still see demos here. And then there are also many follow-up studies and techniques. And also this work is one example of a research project within information visualization techniques. And information visualization itself is a large research field, and you can learn many more from resources available on the net. And also there's a very popular textbook by Edward Taft. It's called The Visual Display of Quantitative Information, and I recommend you to take a look at that book. That's it in this video. Thank you. Okay, our next topic is desktop icons. And the work we will introduce here is called bubble clusters. So the topic we discuss here is a management of desktop icons. So suppose you have a desktop, and then one possible way to organize desktop is use spatial aggregation or spatial clusters. So you put system icons here, and shortcuts here, and some documents here, and documents on other topic here. So in this way, people can manage various information in a limited space. However, a problem is that this kind of visual cluster is not comprehensible from a computer. So they are just icons for a computer's point of view. So whenever you work on this kind of layout, you have to explicitly select group of objects. So that's one problem. Another problem is that you have to, if you put too many icons in the same location, it can cause a clutter. And if you want to grab one icon hidden behind these icons, you have to move other icons away. So that's a problem we want to address. Let me describe the problem. So here you clearly see 4 groups here. However, our system does not understand these kind of clusters. So you have to manually select and move around, and then you should get a new group. Then you have to manually select. So this can be very tedious. Also, if you have a big cluster like this, and then you have to pick up an icon hidden behind it, you have to manually move out and then pick one object. So this is very tedious. So what we propose is bubble clusters. So bubble clusters is automatic grouping of nearby icons, and then visualization of them as a bubble. And also, additionally, we introduce automatic spreading of a cluster to pick up a hidden icon. So let me go back to the demonstration. So here you have 3 groups, and if you enable bubble clusters, you will see these 3 bubbles. And then if you grab a bubble, you can drag them around just by grabbing a bubble without manually selecting a group. And bubble is automatically computed as soon as you place 2 icons nearby. And there's a little bit very small details, but interesting details. Here, these 2 and these 2 are in the same distance. However, if these 2 icons are previously separated, they resist to be merged first. But as soon as they are merged, then they start to resist to be splitted. So this is kind of hysteresis is very useful. and then you can move around and pick up many icons. And then if you have a hidden icon like this, then you can double click here, and then you temporarily spread icons, and then you grab an icon, and then system go back to the original state. So this is a bubble cursor technique, and bubble clusters technique. And then same idea can be applicable to this kind of digital ink. So if you are working on digital ink system, you probably do not want to manipulate individual strokes. Rather than that, each cluster has a meaning grouping. And then whenever you draw strokes, system automatically groups nearby strokes together. And you can move around these strokes by grabbing a blue area. And if you connect together with one object, and then you can draw a line, and you will split them. So this is very useful for a discussion or discussion on whiteboard or digital inks. So that's a demonstration. And let me briefly describe the essence of implementation. So I will first describe clustering algorithm. So we use very, very simple pairwise distance thresholds. So for all objects on the screen, first we assign each object to one cluster. So cluster of object is like this. And then for all object pairs, OI and OJ, if the distance is smaller than a threshold, then they will merge two objects. Here's a view. So for each pair, we check the distance against one threshold, and if they are smaller, we merge them. And the interesting part is here, the threshold. So if previously, in the previous frame, if the objects are in a different cluster, then the threshold becomes very small, so difficult to merge together. And then if the two objects are from the same cluster in the previous step, then it becomes larger, which means very easy to merge together. And after having a cluster, we will generate a visualization of the bubble. And here, what the technology we use here is two-dimensional implicit surface. So implicit surface is to compute potential field around each element, and then trace the isosurface of the field. So suppose you have 1, 2, 3, 4, 5 objects, and then we generate this kind of potential field around it, kind of height field. And then we aggregate them together and then compute isosurface. And here is a visualization. So if you have this kind of icons, and then this one showing the potential field. As you see, if you aggregate more and more objects, it becomes brighter, which means a high potential field. And after that, we just trace lines with the same height. And however, it's very time-consuming to process individual pixels. So we compute potential field values at grid cells like this, and after computing potential field at the grid cells, then we extract isosurface by a technique called Marching cubes. So here's a summary of this video. So the problem we discuss here is a management of spatially organized many icons on desktop. And then solution here, what we propose here is automatic clustering of nearby icons as a bubble. And here's pointers for further learning. So original paper was published as bubble clusters and interface for manipulating spatial aggregation of graphical objects. And the technique we use here is called implicit surfaces. And implicit surfaces are a very popular technique in computer graphics to represent liquids and blobby objects. And the first publication was at SIGGRAPH 82 by Jim Flynn. And then also isosurface extraction technique called Marching cube was published at 1987. And these are very basic literature, and I recommend you to take a look at them. Thank you. Okay, so next topic is pointing. And the work we introduce here is called ninja cursors. The problem we address here is that it's very difficult to point to a long distance object at very far away. So today the screen resolution gets higher and higher, and then the screen gets bigger and bigger, and you can even have multiple monitors. So in such a situation, it's very hard to get a very distant target with a mouse. You have to move a mouse many times to get a target. So this is a problem we want to address. And then we propose a method to address this problem. Let me show you a video. So here we discuss pointing with a mouse cursor. But this can be very tedious if the target is far away, like this way. So you have to clutch mouse many times. So in order to address problem, we propose to use multiple cursors covering the screen. So here we have 4 cursors. And if we have multiple cursors on the screen, you can just use the mouse cursor near the target object. So this can save time for pointing a distance target. So that's the technique we propose in this paper. But the problem is that ambiguity. So if you have multiple cursors and multiple objects in the screen, then it's possible that multiple pointers point to different targets at a time. So this is very problematic. So to address this problem, we allow only one cursor to point some object at a time. So when a mouse cursor is in some object, then other cursor needs to wait until the cursor moves out from the target. So here the user moves the mouse pointer to the right continuously, and then this one goes out, and then this one goes in, and the next one becomes in the waiting state. So as you see, pointing mouse pointers in a queue when trying to point an object. So let me describe again. So the basic idea of Ninja cursors is to cover the screen with multiple synchronously moving cursors like this way, and then the user just use the nearest cursor to the target object. And this one effectively reduces the distance to the target. So it reduces average distance from the nearest cursor becomes from D to D divided by square n. So n is a number of cursors. And this help you to point a distant target. By the way, this is a little bit of background knowledge about pointing. So pointing is a very popular topic in HCI field, and then pointing performance is modeled by this kind of equation, and it's called Fitts law. So suppose you have a mouse cursor here, and then you try to point a target with distance d, and suppose that the target size is w. And then here we consider only one-dimensional motion. And in this situation, target acquisition or pointing time is modeled like this. Time equals a plus b log b, and then inside of log is 1 plus d divided by w. So which means if the distance is longer and longer, then time gets longer and longer with a logarithmic function. And however, the width is bigger, then time will be reduced. So that's the equation. And Ninja cursors, our technique, effectively reduces this d. And as we have already discussed in the video, there is an ambiguity problem. If multiple cursors point multiple objects at a time, this can be a problem. So to address this problem, we allow only one cursor point to a target, and others are blocked and in the waiting queue. So here, a green cursor points to this object, and then this red one in the waiting queue. And then a user continuously moves the mouse cursor to the down, and then green one goes out, and then the red one goes into the object. And we provide a visual feedback, normal cursor, pointing cursor, and blocked cursor. And also, we also provide visual feedback about the waiting time. So yeah, so that's it, and here's a summary. So we discussed the problem of pointing a distant target on a very large high-resolution displays. And then our solution is show multiple cursors and use the nearest one. And we also described how to address ambiguity problems. So original paper was published as Ninja cursors using multiple cursors to assist target acquisition on large screens. And pointing is a very, very popular topic in our field and many publications. And here is a couple of interesting recent papers. One is bubble cursors, and this bubble cursor technique changes the mouse size depending on the target density. So if the target is dense, the mouse cursor gets smaller, but the target is sparse, the mouse cursor gets larger. So it's a very interesting technique. Another is called drag and pop and drag and pick. So as you see here, as you start dragging an object, then related icons jumps to near the cursor position to help you point, to help you do drag and drop efficiently. So that's it. Thank you. Our next topic is digital ink. And the work we introduce here is called Flatland. And the research goal here is design computational augmented office whiteboard. So in many workplaces, there is a whiteboard near the desk or near the working meeting space, and then people take various notes. So we try to provide computational support this kind of whiteboard. And this work started with an observation that office whiteboards are used for informal pre-production activities. So examples are note-taking while you are on a phone, or organizing to-do list, or sketching paper outlines, or discussion with other office mates. So these kind of offline informal discussions are what we want to support. And so this was from user's point of view. From system designer's point of view, what we try to do is to design a computational system that complements current desktop computers. So suppose we have desktop computers and then whiteboards, and these are very complementary. For example, the tasks on the desktop computers are very goal-oriented. You have a specific goal: prepare a document, prepare presentation, make an email, and so on. However, activities on the whiteboard is very informal and very pre-productive. There's no specific goal in many cases. And then operation on desktop computers can be very tedious and complicated because you have to satisfy many constraints. However, whiteboard is very easy. Just pick up a pen and then write down. So it's very lightweight, simple, and easy. And finally, visual representation on a desktop computers are very formal and typed, usually typed text. But however, visuals on whiteboards are very, very informal. So these are the differences, and then we try to support this kind of activities. And so the system we propose have 3 features. And one is a way to manage space, and the other is to applications running on these surfaces, and also history management. So let me show you a demo. So suppose you have a whiteboard and you pick up a pen and then directly writing here. Sorry, I use mouse here, but please assume that I'm using a pen on a whiteboard. And then you can take various notes, such as like a phone number, or you may want to take a note about the schedule, or you may be just like drawings, or you may want to draw a map. And as you see, system starts to cluster nearby strokes automatically. And then you can grab a cluster and then move around. So this is very convenient. You do not need to explicitly group together or not. Or you can manually split 2 clusters away and so on. And one important problem thing here is that visibility is very important. If you have desktop windows, Windows starts to overlap each other soon. But however, visibility is important here, so you should be able to see all information all the time. So as you start dragging, and if it collides with other segment, it starts to push other segments away. So in this way, system prevents overlapping. And if no more space available, it starts to shrink. So in this way, you can still see the content, but you can use a limited screen space very efficiently. And you can just click and then start drawing, and click and start drawing. We also support transition to other sheets like this way. So this is kind of infinite screen connected by horizontally infinite screen space. So this is a screen management. And then next feature is applications. So here is a list of applications we support here. Like you have to sleep, or you may want to eat, and you also need to work. And then you can change priorities, or you can delete them. So here we use gestural interaction using pen gestures. And then another application is map drawing. So you can draw a line and you can get a map, or you can erase and you can get a map. So you just draw a single strokes, but system automatically makes them a map. And one important feature here is that application can be removable. Here it becomes to be a simple plain drawing, and you can add other application like this one. This is a beautification of your informal handwriting. You get this. So another example is calculation. You draw numbers here, and you draw a line, and then you will get the result. We also implemented a 3D drawing. You draw something, and then you can rotate, and then you can cut, and then you can rotate. And if you remove this guy, then you can draw notations and so on. And finally, the last feature is history management. So system remembers everything you do on this whiteboard, and then you can get previous state. For example, if you draw many lines for a long time, and you erase, the system records everything in the database. And then if you get a slider here, you can go back to any previous state in the history, and then you can go jump to the previous state. Another feature is a context-based search. So as I said, system remembers all activities on the whiteboard, and later you can search them just by time or used behaviors or size or colors and so on. And here's an example. So system searches for the previous drawings activities on this whiteboard, and you can get these instantly. So that's the demo. Yeah, here's an example of context-based search. So let me describe the details here. So user input here consists of two kinds. So one is primary input is given by standard ink strokes, mouse left button, and it is always ink strokes. And secondary input, like the other side of pen or pen down with button down, is always a control strokes. And then input stroke is always inking, so it's always a drawing on a screen. And then control stroke is for controlling applications. So it can be a eraser, or can be a dragging of an existing object, or splitting of a segment, or a pie and marking menu. The pie and marking menu is a radially arranged menus. And let me briefly describe the architecture behind the system. So this can be seen as a kind of pen version of standard graphical user interface Windows system. So here's a comparison. So we have standard graphical user interface and our flat land. So standard graphical user interface use a mouse, but here we use a pen. And then standard GUI use widgets and pixels, and here everything is strokes. And graphical user interface use windows, but here we use more informal segments. And then graphical user interface applications corresponds behaviors. And the important thing here is that in GUI, windows and applications are very, persistent object, and application is tightly connected to windows. But here, segments can be merged or split, and also behaviors can be flexibly attached or removed compared to the windows and applications. And here is a structure. In standard graphical user interface window system, data is handled by application. So application encapsulates internal data and then take mouse input and then generates display output using various widgets. In contrast, in our case, behaviors are outside of the strokes, and then it observes the strokes on the board and then add strokes and remove strokes and so on. So behavior works as an attached service to the whiteboard. Here is a little bit more details. So here's a code example of a behavior. So this is plain drawing behavior. So this one takes input stroke and just put in the stroke. And the code looks like this. So add input stroke, handles input stroke, and then just put the input stroke to the segment. So that's a plain drawing behavior. And in the case of map behavior, it takes one stroke and then two-sided street. The code looks like this. So for add input stroke event, the input stroke is divided into left and right stroke, and then these are individually added to the segment. So here's a summary. The problem we want to address is management of multiple informal tasks on an electronic whiteboard system. And then we presented a kind of window system for digital ink with very, very flexible structures. And here's a further reading. The original work was published as Flatland, New Dimensions in Office Whiteboards. And if you learn more about gesture recognition, there are a couple of pointers here. The Rubine's specifying gestures by example is a very original work on example-based gesture recognition, which was published in 1991. And the recent one is, one example recent one is Gesture Without Libraries, Toolkit or Training, $1 recognizer for user interface prototypes. And also, I showed pie menu and marking menu here. And this is interesting widget popular in pen computing. And I also recommend you to take a look into this literature. Thank you. Hello. Topic here is voice interaction. And the work we introduce here is voice as sound. So here's the background, motivation. So we see there are two aspects in our voice. So one is verbal information and the other is non-verbal information. And typical speech interaction use verbal information, such as they convert your speech into recognizable command and then do something. But however, on the other hand, our voice also contains non-verbal information such as pitch, volume, speed, and so on. So these non-verbal information has been ignored in traditional speech recognition. But here, what we want to do is leverage this non-verbal information in your voice. And here is a kind of concept. So interaction turnaround is very long in traditional voice or speech recognition. So you say something, and then computer tries to understand it, and then you say something, and then system tries to do something. And this is very, very time consuming, and it's very discontinuous. On the other hand, for example, if you are working on a mouse, and if you grab an object, you continuously move your mouse cursor, and then the system continuously provides feedback. So this kind of direct manipulation experience is what we want to achieve using computer. So in our technique, the user continuously makes your voice, and then system continuously provides feedback to your vocal input. So let me show you a video. So here we introduce 3 techniques. The first one is most simple on-off button. So here your voice works as on-off button. So if you say nothing, it's off. If you say something continuously, it means you press button. Here's an example. So here, typical approach is the voice recognition. So if you want to move this knob, say maybe you say 30 degree and you get result here, and 90 degree you get result here. But again, if you use voice recognition, interaction can be very discontinuous. Here, your voice is a switch. So if you make voice, this one starts moving. As soon as you stop speaking, it will stop. So you can continuously see the visual feedback. So as you see, you can continuously get feedback. So if you get a satisfactory result, you just stop speech and you get the result. And if the voice is very annoying or difficult to produce, you can make any noise. So you can use a breath to control a system.
Down.
And if you combine this with traditional speech recognition, you can do something like this. Again, traditional approach is to say like 100 meters away or 1 kilometer away and so on. But it's kind of difficult to understand what's going on. But here, you just speak and then stop speaking. And this is especially useful for zooming. Zooming 1.2 is very difficult to imagine. But here, you just see it.
Right. Zoom out. Up.
Okay, so that was a first technique. And here is the second one. Second one is, in addition to on and off, you can also control a parameter using a voice, using a pitch of your voice. So let me see. So you control a slider with the pitch of your voice. So it's very, very stable. That's the most important part. So here, in addition to controlling a distance, you can also control a speed of the scrolling.
Right. Up.
Again, higher the voice, the faster you move. So far, I showed very continuous control parameters. But here, the last one is discontinuous, discrete control by tonguing. So suppose you want to change TV channel or something like that.
Down. Ta 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 ta. Left. Ta ta ta. Up. Ta ta. Right. Ta 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 ta. Down. Ta ta ta.
So here we use very, very basic signal processing. So you can do any noise. So you can also clap your hands to control it.
Down. Right. Right.
So that's 3 techniques we introduced. And then next I will show you a couple of entertainment applications of these techniques. The first one is jumping game using a voice. So next one is using pitch control to control the vertical position of this fish. The last one is like punching game using a voice. So that's it, and let me go back to the slide. So let me briefly describe the implementation of this kind of system. First, we use signal processing techniques, and we use existing Fourier transform library. So it transforms input voice signal data into frequency domain. And then application is control is implemented in Java. And the first technique, on and off control, is very naive implementation we use. It just checks total volume, total power of the input signal. And if we check whether the total volume is larger than the threshold or not. One implementation detail is that we ignore low frequency part to suppress background noise. And important part is the pitch detection. So we use voice pitch to control parameter up and down, but this needs to be very stable. A naive approach is to identify absolute pitch for each voice. So here is the input signal, and then try to identify the dominant pitch. However, this is very difficult. It's very ambiguous, noisy, and unstable. Please imagine that this kind of frequency signal is changing all the time, and then it's very difficult to identify a peak. So at some point this is the highest, but the next moment this one gets highest. So it's very unstable. So this naive approach works very well. So our approach is to just all checks slightly up or slightly down at each frame. So in this way, the result is very stable. So we only check whether the pitch is getting higher or lower a little bit. So here's a detailed algorithm. Suppose you have this kind of spectrum at time t0. So the vertical horizontal axis is frequency, low frequency to high frequency, and for each frequency you get amplitude. And then you get another signal at t0 plus dt. And then your task is to detect whether this frequency signal is shifting downwards or upwards. So in order to do it, we get this, we aggregate this signal into a vector, and then in the next time, for the next frame, we get a vector for the shifted upwards and also shifted downwards. So you have three vectors. And then we just compute dot products between them. So this one is dot product between V and V minus. And then you compute also V and V plus. So, and if V minus is higher, then V minus is more closer to V. So which means that the pitch is shifted lower. And then if this dot product is V plus is higher than V minus, which means that V plus is closer to V, which means the spectrum gets higher. So this very simple implementation returns a very stable result. So here's a summary. So we discussed the problem of controlling object continuously using your voice, using nonverbal features. And then our approach is to use a nonverbal aspect of your voice. And the original paper was published as Voice as Sound, a nonverbal voice input for interactive control. And multimodal interface using gesture and voice is also a very popular topic in our field. And the very original paper was called Put That There. So you say put and then say that, showing some object. And then again say there, and then showing another object using your gesture, and then you get the task. And the video is available on the YouTube, so I recommend you to take a look at it. And also there are a couple of interesting voice-based interaction techniques, and one recommendation for you is speech completion, and this one tries to complete your speech in the middle. And also video is available, so I recommend you to take a look at it. Thank you. So this is the end of week 1. The topic we discussed in this week was graphical user interfaces, And then we discuss scrolling interfaces, the management of desktop icons, pointing techniques on the large screen, and management of digital ink. And then finally, we discuss voice interaction. Thank you.